We now introduce what we are going to look at as the principles behind the method of Lagrange multipliers. And this is the method we're going to use on these constrained optimization problems. Now, there are going to be two ingredients in a method or an optimization problem of this type. One is going to be our function that we want to maximize or minimize, and the other one is a constraint. And notice how the form of this works. It's some relation on x and y, or in this case here a function of x and y, must equal some particular constant. So we saw in earlier examples this would be the points on a sphere, so x squared plus y squared plus z squared must equal some constant radius squared. Our constraints can almost always be put into this form, and we're going to use another insight that this is another way to write a contour of g of x of y. And so we're going to have to take a step back. A constraint we don't usually think of as a function, we think of it as a set of points. But we can, if it is helpful, think of it as some function equals one constant, which gives us one contour of this g of xy function. Here's the kind of picture we're talking about. Our function, which might have 10, 20, 30, 40, 50, 60, so we see these contours here, the f ones, these s-bend ones. If we consider that scenario, then if we wanted to go higher in higher in f, then we would head down towards the bottom here. That would be the optimal place to go. Here's our constraint. G of xy is a constant. That is limiting us to only being, for this example, on this circle here. So if I could pick any xy I wanted and I wanted to find a big F value, I would definitely head down this way. But I'm only allowed to walk along this circle. So think of it as a map. I've got a fence, or I've got a little path. I'm only allowed to walk along this path. Then, well, we can actually see if I was to walk along this path and I wanted to get to the highest F value, I could be here, and that is at F30. I could move further down. I'd be getting closer and closer to F40. And in fact, that point right there where I touch f equals 40 seems like the highest value we can reach. Now, one of the questions we might ask is there something special about that point that is not true of the other points? And there is, actually. If we consider what we know about optimization, gradients are important. So let's ask ourselves what the gradients are. I'm going to erase our line here for clarity. We should ask ourselves what our gradients are at different points in f. So let's only consider the points we can actually use. But if I want to calculate the gradient at this point here for f, it would be perpendicular to the contour and pointing uphill. So I'm going to put all of these arrows here. These are going to be the gradients of f. And likewise here and here, perpendicular, perpendicular, and as we go along, there's another contour here. So those are all our gradient of f values or directions for points on this constraint. So I'm only allowed to pick points here, and I can find the gradient of f at any point on that curve. Step 2. What about treating g of xy as a function? Well, if we treat that as a function where k is just one of the values that we can pick, we would also get curves inside and curves outside. Let's imagine k is our radius, so the radius gets bigger as we go out. We can actually draw gradients not of f now, but of the second function g, just to get directions that are perpendicular to the contour. Well, in that case here, if they're going to point out, they're going to point perpendicular to the circle here, and perpendicular to the circle, and I guess I can draw these ones I can draw wherever I like, but we'll try to draw them at the same kind of points we used before as well. There we go. So we can get the gradients of this function anywhere we like. Now remember, if we had our druthers, we'd pick f up here and we'd be finding much higher values of f than we can given this constraint. But if we're only allowed to walk in the circle, what looks like our best point is right here. because the function f is getting higher and higher and higher as we move down here, and the furthest point in that direction I can go on the circle is where this black dot is. And what do we notice there? This is at the max of f on the contour, g of xy equals k. So of all the places I'm allowed to pick, that gives the highest function value, and at that point, the gradient of f is parallel to the gradient of g. If you look at these other points, which are not as good, then we see that the gradients are pointing in opposite directions. But here, because we're just touching the contour of f, and we're coming out and these two contours are tangent basically, then we're getting something special happening. What's happening back here is I've got my circle, and I can move along that circle, and if I move in this direction here, the direction roughly towards the gradient, I can go higher on f. But by the time I reach here, the only way to go further up is to walk off the circle, or go perpendicular to the circle. I can't do that, so this must be, in some sense, a maximum or a minimum. We also see the same issue here at the opposite side of this circle. This is at a minimum of f on the contour of g. So if I wanted to go downhill at this point, well, I should move opposite the gradient vector. I can't move perfectly in that direction, but I can move some component in that direction, and I can still move down, move down, move down, move down. Once I get here, though, the only way to go further down is to go perpendicular to the restriction that I'm on, this circle. I can't do that, so I must be at the lowest point I can reach, at least locally. And that inspiration is what we're going to use to create equations. So this is the graphical interpretation of what we would like to do, but we're going to use this to generate equations that let us solve for these points based on this observation that at the maximums and minimums of our function on a constraint, the gradient of the constraint function and the gradient of our surface are going to be parallel to one another.